So now you have something called as the program counter. So we see about the MIP state elements first. So first element, the state element is going to be the program counter. So the program counter is 32-bit register over here. So its work operates on the clock frequency. And next is the instruction memory. So instruction memory, it's going to take the address, 32-bit address from the instruction, and then it's going to read the 32-bit data. So sometimes it's going to be the instruction in this case. So from the address, it's going to read the instruction from that address, and to read, and it is going to read the data output from RD. So this is the function of this instruction memory. Next, we have the register file. Again, this is a 32-bit element. So it has got two ports, two read ports and one write port. Signal which is going to tell you, confirm whether it is a read operation or the write operations. So you have the enable operation here, so which is 3 bits. So the combination of this, the write enable is going to tell you whether it is read 1, read 2, or it is write operation. So similarly, you have data memory. So this data memory, again, it works in the clock cycle, and it read and single write port. So if you enable this write, if it is 1 high, then it is going to write the data into the address A, which is given from the 32-bit address, and on a rising edge it's clock. So if you write this enable is going to be 0, then it is going to read the address onto the read. So from this data address, it is going to, so this is all latched concept. So we are latching whether it is write enable is latched or unlatched. So on a latch, or when it is high, it is going to be the write operation. When it is low, it is going to be the read operations. So these are going to be the basic MIPS. The MIPS elements. So now we'll understand the microarchitecture. So based on, we have seen based on the MIPS elements, state elements, how they are connected together. So in that aspects, we have some 3 basic classifications of this microarchitectures. The first is the single cycle microarchitecture. Second one is going to be the multi-cycle microarchitecture, and next one is the pipeline microarchitecture. So if you see with respect to your single cycle microarchitecture, it is going to execute an entire instruction in one cycle. Yes. So and it has got some simple control unit and does not require non-architecture. Cycle is going to be calculated based upon the slowest instruction. So say for instance your load word is going to be the slowest instruction for that format, then your cycle time is going to be based upon that load word instruction. So it is going to execute instruction in series of shorter cycles. So irrespective of your slowest instruction, your instructions are going to get executed in series of shorter cycles. So the simple instruction execute in a fewer cycles than the complicated ones. So it now, when it is going to execute it in fewer cycles, what happens is that it reduces the hardware cost by reusing the expensive hardware blocks. Say for instance, if many blocks can be sort out by using of multiplexer or a demultiplexer. So those ways are going to be coming into picture. So you are trying to reuse the expensive hardware such as your harder adders and your memories. So by this way, your hardware costs get reduced. So it uses non-architecture registers to hold the intermediate results. Yes, apart from here, it does not use any intermediate results. It's not being stored. Wherein your multi-cycle architecture goes with usage of non-architectural registers to hold up the intermediate results. So say for instance you have a carry, then it has to hold some in the temporary or temporary memory locations. So it uses the intermediate results. using the non-architectural registers. So it executes one instruction at a time, but each instruction sensors. So that is the prime difference between your single cycle microarchitecture and multi-cycle microarchitecture. So next, looking into the pipeline microarchitecture. So it is going to apply the pipelining to the single cycle microarchitecture. So what happens is that if you're it can at a particular given time, it can execute several instructions simultaneously. So that is the character of pipelining for that matter. So it simultaneously, improving the throughput significantly. So you are going to execute the given program in a very limited amount of time. So the number of to execute the same program in the single cycle microarchitecture is going to drastically vary if you're going to use with pipeline microarchitecture. So the pipelining must add logic to handle dependencies between the simultaneously executing instructions. So there is sort of these dependencies between the while executing the simultaneous instructions. So it also requires non-architectural pipeline registers, as we have seen, in order to hold the intermediate results. So all high commercial performance processor will be using pipelining architecture in their processor design. Yes. So now let's see, understand in detail about all these three architecture with an analogy. So now we'll have the processor analogy with that of a laundry example. So here we'll see what is the analogy between the processor and the laundry process. So the first one is so instructions are transactions that execute on a processor. Okay, the instructions are transactions that execute on a processor. So this architecture is going to define the hardware or the software interface. So microarchitecture tells you how hardware executes a sequence of instructions. So similar to that, if you see, so now here in the laundry example, we see the cleaning of a load of laundry is called the transaction. So analogy to the architecture is the high-level specifications like dirty clothes in, clean clothes out. So this is the high-level specification, very analogous to the architecture. When you look into the microarchitecture, how your laundry room actually processes the multiple loads. So if you're going to analyze them, then that is going to come under the microarchitecture analogy. Yes. Further, let us walk in through this, comparing this analogy with that of your laundry example. Say, for instance, we have 4 customers. So Annie, Ben, Kathy, and Dave. So we have got 4 customers. So your laundry, the first operation is going to take, each of the operations are going to take place in 30 minutes. So first step of the laundry process is going to be washing, followed with drying, followed with folding. 4 operations that we are typically considering in a laundry operation, which is going to compose 30 minutes each. So go for all the 4 operations: washing, drying, followed with folding and storing. So Ben has to do only 2 operations, only washing and drying. So washing and drying, Ben prefers to do to his laundry basket. And Kathy's load is to perform 3 operations. So one is washing, drying, and folding. So and Dave has got to perform all the 4 instructions. Looking into the transition latency, what happens since each of the operations are going to take place in 30 minutes, your Dave's operation, the maximum latency will be 2 hours. So the maximum latency in order to complete Ben's load is 1 hour, Kathy's load is 1.5 hours, and Dave's load is 2 hours. So these are the 4 steps that we are trying to carry out in different microarchitectures. First, see what processor. So in the fixed time slot single, so the time slot is the slowest operation is taken as a time slot. The slowest operation or the maximum time consuming operation is either Ben's or Dave's, which is in which all the four tasks are performed in the laundry process. So you have washing, drying, folding, and storing. All the four operations. So this is going, the dates load is going to determine what is the time slot. So it is 2 hours time slot for Annie's load. So it is in a single fixed time slottery. Um, After this 2 hours is complete only, it is going to take up the next person's load. So you have Annie's load to complete it in 2 hours. So after the process of storing of Annie's load, then only it takes up the Ben's load, and process to carry out in this laundry process, the remaining time slots are kept empty. Okay, so that is with respect to your fixed time slot single cycle process. So next you have Kathy's load to be performed. So Kathy's load is performed again. We have only 3 operations. So 1 time slot, 1 half-an-hour slot is left like that. And after this 2 hours of time slot, then you have. So this is the point that you have to understand in a fixed time slot laundry. So next we have, we understand the variable time slot laundry. So in this variable time slot laundry, which is your Fsn processor is going to handle. So here you have Annie's load is going to do all the 4 processes: your washing, drying, your folding, and storing. After the completion of the 4 tasks, then it takes up the Ben's load. So Ben's load does not have the last 2 processes. So the first 2 processes, which is washing and drying process of Ben's load is done, it takes up your Kathy's load. So Kathy has got again 3 processes to do in this laundry operation. So after these 3 operations or the process is carried out, that is after your folding phase, you have Dave's load taken up. So in this way, that is the difference between your single slot cycle processor and your variable time slot cycle of your processor. So next we'll see understand what is pipelining. So pipelining is very interesting, which is followed in almost all the cases of your nowadays computer. We have pipeline architecture that is being followed in the processor design. So here you have to understand here Annie's load has to do all the 4 tasks. So when you see, once the washing of Annie's is done, it goes for the washing operation. When you have washing, the drying phase of Annie's is taking place, Ben's washing phase takes place. So when your folding phase of Annie's is Ben's is taking place. So when you see, once the washing is done by Ben, then Kathy's is taking place. In the drying phase of Annie's, so you have Kathy's operation of washing is taking place. So this is that when one instruction is executing something else, your second operation, the first operation of the second operation of the first. Similarly, when the second operation of the second customer is being performed, we have the first operation of the third customer being performed. So this is the case of pipelining architecture. By this time, you'll be able to finish your entire program. So if you're looking for the operation of the executing a program, then you have to understand when one instruction. So this is a typical example that we are trying to follow in modern day computers. So this is called as the pipelining architecture. So let's understand in terms of processor. So performance, we have something called as your time per running a program. So your time per running a program will depend upon the instructions per program into the average cycles per instruction, and to run or execute a program is being calculated. So if you understand this, your instructions per program depends upon your source code, your compiler, and your architecture, instruction set architecture. Similarly, your average cycle per instruction is going to depend upon your instruction set architecture and the microarchitecture. And what is the microarchitecture that you're going to follow? Whether it's going to be single cycle processor, your FSM processor, or your pipeline processor. Similarly, your time per cycle depends upon the microarchitecture and the implementation. How optimized you write the code. So that is how your processor performance is being analyzed. So typically, you have got a greater role to play in your microarchitecture in designing, improving the performance of your processor. So looking into it, you have the single cycle processor, which is one, which executes single it uses cycles per instruction is one. So the cycle time will be long, as you have seen in your laundry operation. Next is your FSM processor. So your number of cycles per instructions is greater than one. So your cycle time becomes lesser. Similar to your pipeline processor, it is greater than or approximately equal to one. So it is again shorter. So this is how you are analyzing your processor performance. So here, analogy to that, we have drawn typically represented your single cycle processor, your FSM processor, and your pipeline processor, how it is going to execute. So this is with respect to analyzing your processor. Next, we have. So what is a cycle? What typically a cycle is going to do? So instructions are processed under the direction of which is asking us to, which is going to generate control signals, asking us to perform a particular task. So instruction cycle is a sequence of steps to process an instruction. Now we have to understand that there are six in the execution of an instruction. We have got typically 6 steps. First is fetching the instruction. Next is decoding the instruction. Next, which is followed by evaluating the address and going to that address and fetching the operands, and now performing the operation, that is executing the operation and storing the result. So these are typically the 6 steps. So in a instruction processing cycle, these are the fundamental 6 steps that are being followed. But there are certain instructions like your jump instructions which need not require all the instructions to be performed, all 6 steps to be performed in executing an instruction. So typically based on your instructions that you're working, either of the 6 fundamental steps. So with respect to that, we have instruction processing. So instruction processing engine consists of 2 main components. So one is data path and the control logic. So this data path is going to consist of hardware elements that deals with and transform the data signals. So these are going to be the elementary functional units that operate on data. So your data transfer is happening through this hardware elements. So this is going to be the functional unit that is going to operate on data. Next, we have hardware structures like your wires, which is going to enable the flow of data, or it's going to be the MUX, which is going to enable the particular data to be transferred to the next unit. So the hardware structures like your wires and the MUXes that enable the flow of data into the functional unit coming under this data path. Next, you have the storage units. So storage units are typically the registers that stores the data. So this is with respect to your data path. So similar to your data path, you have in the instruction processing, you have something called as the control logic or the control path. So this is going to contain or consist the hardware elements that determine the control signals. So this signals that specify what data path element should do to the data. So that is determined with this control logic. So this is the typically instruction processing components. One is the data path and the control logic. So that is single cycle and the multi-cycle with respect to your control and data. So your in single cycle machine, what happens is that the control signals are generated in the clock, in the same clock cycle as that of one which data signals are being operated upon. So all happens in the same cycle. So everything to a instruction, everything that is very closely related to the instruction, be it your place in one clock cycle. Okay, but with respect to multi-cycle machine, what happens is that the control signals needed in the next cycle are generated in the current cycle. So the latency of control processing can be overloaded with the latency of the data path. So your next cycle, what are the controls are required, are generated in the current cycle in the multi-cycle machine. Whereas both the control and the data signals are operated in the same clock cycle. So that is the prime difference if you're talking about the single cycle and the multi-cycle operation. It, uh, left outside. Next, we have the transactional steps. So we can think of each how we are going to achieve executing the instruction following this sequence of steps. Say, for instance, we have these many transaction that has to happen in executing an instruction. First is the fetching the instruction, then you have to decode, then read the registers, then read register arithmetic in order to, these are the that is stage elements of the MIPS. Then you have to read from the memory, it's write from the memory, write register, update. So these are the either of the things transactions would happen. Say for instance, in your add instruction, your fetch, decode, read register, anything to do with your read memory or write memory directly to your registers we have, since they are register based instructions, R-type instructions. Similarly, when you look into your load word or store word, when you compare, you have fetch, decode, read register with read memory operation, wherein your store word operation instruction will go with your write memory and you have the update of your counters, program counter. So typically you don't have much of operation to do with your jump instructions. So in your jump instructions, you have jump right or jump arithmetic left is going to do fetching, decoding, write to the register, and they update your program counters. So that is being followed in each of the instructions. So typically, these are listed are the few of the instructions, and they are sequence of steps that are followed in execution of each. So this we will see it in the next class, which is related to single cycle data path with respect to your load word fetch. Load word is the instruction we'll take up, and we'll understand how the single cycle and pipeline architecture are going to work. Any doubts so far? Okay. If no doubts, we'll wind the class for today.